Hello everyone, my name is Luca Del Pero. I am an engineering manager at Lift Level 5, where I work on our program for mapping and perception from commodity sensors. In this section, I will talk about the data requirements for Autonomy 2.0. What type of data do we need and how much do we need? How can we get it and what are the main open questions? So far today, we have seen that Autonomy 2.0 is about injecting machine learning throughout the autonomy stack, including components like planning and prediction that are traditionally tackled with rule-based systems. The promise is that machine learning can help us solve some of the toughest problems in autonomous driving by leveraging data. For example, this recent machine learning planner gets better as we train it on more and more hours of sensor data. And access to large amounts of data will be key for the success of Autonomy 2.0, as it is the case for other fields based on machine learning. The key questions here are: what type of data do we need and how much? In Autonomy 1.0, the main machine learning piece of the stack is perception, whose goal is to detect objects and obstacles in the 3D environment around the SDV. We saw earlier in this tutorial that we can build very robust perception systems by training them on sensor data with labeled 3D objects. However, Autonomy 2.0 uses machine learning further down the stack for planning and prediction, and these systems are trained quite differently compared to perception. For example, machine learning planners learn driving policies from behavioral data. That is to say, these models learn to plan from the behaviors chosen by drivers facing real-world situations. For example, they are trained on the trajectories that these drivers choose to follow. And the need for behavioral data is a very important requirement for Autonomy 2.0. In fact, most of the behaviors we observe on the road are not particularly interesting, as most driving is easy and uneventful, with cars driving down a road with nothing happening for hours. However, if we want ML systems to drive safely in any condition, we also need to observe a lot of the more rare and challenging driving scenarios. And this will likely require collecting many million miles of sensor data. How do we collect such large amounts? One option is to rely on the SDVs used for Autonomy 1.0. which are equipped with multiple HD sensors like LiDARs, radars, and cameras. These sensors provide accurate perception, which is a key requirement of the rule-based systems used in Autonomy 1.0. For example, a rule-based planner requires very accurate perception in input to work. However, these HD sensor solutions are typically expensive and do not scale well. Think, for example, of HD LiDARs. Another option is to collect sensor data using commodity sensors like cameras, which scale well, but provide less accurate perception. For examples, from cameras we cannot detect objects as far away or as precisely as we would from HD sensors. Essentially, we are faced with a trade-off between data quantity and perception accuracy. Sensors that today scale well give us higher quantity but lower accuracy, while HD sensors give us higher accuracy but lower quantity. Understanding this trade-off is important, as it helps find ways to get enough data for Autonomy 2.0, and it also helps us understand which sensor we should use to collect this data. And this is precisely what I will discuss in the second part of the talk. First, I will make the trade-off I just introduced more concrete by looking at the data quantity and the accuracy we can expect from existing sensor solutions. Then I will look at the problem from the opposite perspective, that is to say, what perception accuracy does Autonomy 2.0 actually need, and hence which sensors. Last, I will discuss how we can use transfer learning to mix data collected with different sensor types. Let's start by comparing existing sensor solutions. This table shows results from the Kitty leaderboard, which is a standard benchmark for perception. The perception accuracy metric is called mean average precision, or MAP, which compares the 3D position of the objects detected by perception to their ground truth position, which is manually annotated. Solutions using monocular cameras, like the one in the top row, are the most scalable, but have a significant accuracy gap compared to HD LiDAR in the bottom row, which achieves 3 times higher MAP. Solutions with stereo cameras start to be competitive in terms of accuracy, and the accuracy gap is further reduced if we add sparse LiDARs, which are still not prohibitive in terms of scalability. One thing I find encouraging is that closing the quality gap between HD and commodity sensors is a very active area of research. For example, today's best monocular methods is 4 times more accurate than the best one from 3 years ago. And I also want to point out that while HD sensors today do not scale well, we can also expect that hardware advancements in the next few years could mitigate this problem. To recap, I just covered what we can expect from existing sensors in terms of scalability and perception accuracy. However, how much perception accuracy do we actually need? In the Autonomy 1.0 world, we assume that rule-based systems need very accurate perception to work. And we measure perception accuracy with mean average precision, which we just saw measures how well perception does 3D object detection. It is unclear, though, whether Autonomy 2.0 needs the same levels of perception accuracy as 1.0. Does an ML planner have the same perception accuracy requirements as a rule-based one? In a stack where all components are ML-based, can we make up for some inaccuracy in perception by training the perception and the planning system together? These truly are open questions. An interesting idea that can help us here is to start evaluating perception more end-to-end. For example, by looking at how it impacts planner metrics. The intuition is that if a perception system enables the planner to consistently make safe planning decisions and choose optimal trajectory, it should mean that this perception system is accurate enough, even if it does not reach an arbitrarily high MAP target. Object detection metrics like MAP are good proxies and are reasonably easy to interpret, but they do not directly measure the impact of a perception system on the downstream task of driving. Relying more on end-to-end metrics is a way to help us understand what perception accuracy we need for an ML planner, and hence which sensors we should use. And let me finish with one more idea for scaling data for Autonomy 2.0, which is transfer learning. Imagine if we could collect data at scale with commodity sensors and then use it to train the systems of an SDV that at test time is equipped with different, potentially higher fidelity sensors. This would give us a way to scale data collection because we could mix data collected with different sensor types. Recent work has shown promising results, including work that uses transfer learning from simulated data. This is work we published this year at ICRA, where we took an ML planner that at test time always uses HD sensors providing accurate perception, but it is trained on data with lower perception accuracy, which is what you would get from more scalable commodity sensors. An interesting takeaway is that at test time, the ML planner performs better when it is trained using 100 hours of sensor data with low quality perception compared to when it is trained on 10 hours of highly accurate perception. So in this case, data quantity trumps perception accuracy. This shows that transfer learning is a very promising path to scalability because we can get value from data collected with scalable commodity sensors, and we can mix data from different sensor types. To recap, while there has been recent progress in understanding the data needs for Autonomy 2.0, a lot of the topics I covered today still have open questions. First, the perception accuracy gap between commodity and HD sensors is getting smaller, but how much more can we expect it to shrink? Second, in the Autonomy 2.0 world, we should look at the assumption that we need HD sensors with an open mind, since machine learning models might not need the same levels of perception accuracy as rule-based ones. And third, transfer learning is a promising way to leverage data from commodity sensors, but its full potential remains unclear. And these are all important questions we need to address to understand how to meet the data requirements of Autonomy 2.0. Thank you very much for your attention.